Welcome back, everyone. This is Mr. V. Hill, and today we're going to talk a little bit about exponential decay. First, we're going to review exponential growth just a little bit, just because I took a little detour there and talked about some compound interest versus simple interest, but we also saw that compound interest was an example of exponential growth. So the basic model for exponential growth is, of course, y is equal to a times b to the power of x, or y is equal to a times 1 plus r to the power of x, or b and 1 plus r are the exact same thing, and where a is the initial amount, b is what we call the growth factor. That's the thing that we're multiplying by over and over and over again. That repeated multiplication is what becomes the exponential expression right there. Or if we want to write it as 1 plus r, r was what we call the growth rate, meaning the percent increase that occurs each time period, be it a year, a day, a month, whatever. But for this to be exponential growth, what we needed to have was the constant multiplier, or the growth factor, to be bigger than 1. Because if you multiply a number by something bigger than 1, it gets bigger, or it grows, right? Or in order to get b to be bigger than 1, r just has to be a positive. So we add a positive number to 1, well, we're going to get a number bigger than 1. Right? No big deal. So for example, if we had an exponential growth of, say, like y is equal to 500, that's our initial amount, times 1.2 to the power of x, meaning we're going to multiply by 1.2 every time period, meaning it's going to be increasing, of course. It's going to be increasing by this 0.2, or 20%. The 1 refers to the 100% of the 500 that we're going to be getting, and the 0.2 refers to the 20% more that we're going to be increasing by. And we're going to be increasing by that 20% each and every time period. So here a, our initial amount is 500. B, the constant multiplier, or the growth factor, is 1.2, or we could think of that as 120%. And r is 0.2, or 20%, the amount that we're increasing by each time period. And so if we just want to look at this, I want to figure out, well, how much is there going to be available to it, or what is going to be the amount of this population, or whatever it is, at a certain time period. All you do is just type it in and say, well, if we want to, after 5 years or 5 days, whatever that is, 500 times 1.2 to the power of 5. So after 5 time periods, we're going to end up with 1,244.16 for the value of y. Or if we wanted to, we could just put this into a table and just type it in here. Y is equal to 500 times 1.2 to the power of x. Then maybe we could look at a table. So here, when x is 0, no time has passed, we still have 500. We haven't started growing yet. After 1 time period, we get a population of 600, which is 20% more than 500, right? Because 20% of 500 is 100. So we increase by 20%. 500 times 1.2. After 2 time periods, well, of course, we'd have 720, because 20% of 600 is 120. We tack that onto the 600, or we could think about that as 500 times 1.2 times another 1.2, or 1.2 squared. After 3 time periods, so we get 864, and that should come about from, well, multiplying this previous value by another factor of 1.2, which would make the expression 1.2 cubed. And if we wanted to, we could actually look at this as graph maybe and see what happens here. So we look at, if we want to go out for 20 time periods, you see we'd end up getting almost to 20,000. That's a pretty big increase. So if we wanted to graph this thing, we should change our window around. And if we're going to go out 20 years, well, we don't need any negative amount of time. So the x, the number of years, is going to go from 0 to 20. And we want to get up to 20,000 about on our graph, so 0 to 20,000 for the y's. There's, of course, no negative values in here. And I changed the scale to every 5,000, just so we can see this a little bit better. So let's just graph that, and here we see our nice exponential growth curve. Starts off climbing slowly, but as time passes, it starts increasing faster and faster and faster. That's your exponential growth. Okay? No big deal. Now for exponential decay, things are going to change just a little bit. Basically, we're going to have the exact same model. Y is equal to a times b to the power of x, where a is, of course, the initial amount, and b is going to be what we call the decay factor this time. So again, it's what we're multiplying by each time period. But now if we want to diminish the population or have it decrease as time goes, then we can't multiply by something bigger than 1. Because multiplying by something bigger than 1, well, that's exponential growth. Here we have to have the decay factor being less than 1. Because if you multiply a number by a value less than 1, it's going to decrease, right? Even if it's just slightly less than 1, if it's 0.99, it's still going to decrease. But now we need to see how we're going to get this decay rate going on here, R. Because that's going to be the percentage that we're losing each time. And that's pretty simple. So we just rewrite this as y is equal to a times, now instead of b, well, b is going to be less than 1, so we need to subtract off some positive value from 1. b is now going to be equal to 1 minus r. So we have to subtract off some positive value from 1 to make sure that b is less than 1. Should make sense, I hope. So for example, suppose instead of increasing by 20% each time period, we want to decrease by 20% each time period. Pretty easy to do. The model would be y is equal to, we'll start with the same amount, 500. But now if we're losing 20%, that means we're keeping 80%. And 80% we can, of course, write as 0.8. And that's going to be what we're multiplying by each time period. So that repeated multiplication is what becomes this exponential expression right here. Or if we want to write it this way, to focus on how much we're losing instead of how much we're keeping, we can just rewrite this 0.8 as 1 minus 0.2, still to the power of x. So here, again, a, our initial amount, is 500. B, the decay factor, is 0.8, or 80%. And R, the decay factor, the decay rate, is going to be 0.2, or 20%. Initial value is 500. The decay factor is 0.8. The decay rate is 0.2. We're keeping 80% looking at it with B, or we're losing 20% by looking at it with R. And if we want to look at a little table of values there, let's just change this up. Let's delete that out. Okay, so 500 times 0.8 to the power of x. Again, we just look at a table first. Going back up to year 0. Start off with 500. After one time period, we've lost 20%, or we've lost 100. We get down to 400. After another time period, we've lost another 20%. 20% of 400 is 80, of course, so it dropped down to 320. No big deal. And so if we want to figure out what the population is going to be after a certain time period, all we got to do is plug in a certain value of x and see what y is. Or if we want to look at this as a graph, that's not a problem. We probably want to change up the window a little bit because we're going down. So our x max would be 0. We'll go at 20 years or 20 time periods again. The y max, let's put that at 500 because we're decaying from 500. And we put a tick mark every 100. And let's see what kind of graph we get here. And there we see our nice exponential decay. Still an exponential curve, but now it's decreasing as time passes. Getting closer and closer and closer to 0. Not a big deal. That's all exponential decay really is. So let's look at an example of applying this. So we're going to start off with a city, and it's going to have 800,000 people living in it at time 0. And the population is declining at a rate, that's your R, of 25%. 25% or 0.25. And we want to know what the population will be in 4 years. Well, it's pretty easy to do. We just set up our exponential decay model. Y is going to represent the population. Our initial value is 800,000. Now we're going to be multiplying by 1 minus the decay rate, which is 0.25, written as a decimal, to the power of x. We could, of course, if we wanted to think about this, instead of losing 25%, we're keeping 75% of the population each year, or each time period. So we could write it this way as well. 800,000 times 0.75 to the power of x. Here we're focusing on the decay factor. Up here we're focusing on the decay rate. Not a big deal. So after 4 years, all we need to do is just plug in 4 for x. Y is equal to 800,000 times 0.75 to the power of 4. 800,000 times 0.75 to the power of 4. And we're going to end up with our new population after 4 years being 253,125. Fairly simple, right? Let's look at another example. So now we have a dose of antibiotic injected into your bloodstream. Initial value, putting in 10 milligrams. And the decay rate is going to be 16%, or 0.16. And now after 4 hours, this time not years, 4 hours, we want to know how much of this antibiotic is still going to be in your system. Well, again, just set up your exponential decay formula. Y is equal to the initial amount of 10 milligrams times 1 minus 16%, or 0.16, raised to the power of x, where x represents the number of hours. If you wanted to, you could, of course, just write this as y is equal to 10 times 1 minus 0.16 is, of course, 0.84 to the power of x. And so here is the decay factor of 84%. So every hour, you're going to be left with 84% of the previous amount. Or up here, we're focusing on the decay rate of 16%. So we're losing 16% each hour. And we just want to know, well, what is y going to be when x, the number of hours, is 4? 10 times 0.84 to the power of 4. Use our little calculator here. 10 times 0.84 to the power of 4. And we're left with 4.98 or so, so about 4.98 milligrams, or almost 5. So they've just dropped below half the amount after 4 hours. Let's look at one more example. And actually, the whole leaving ourselves with half the amount leads us to the next little item that we want to talk about, which is called half-life. And so half-life is just the amount of time it takes for 1/2 of a substance to decay into another substance. So we use this in radioactive decay. Oftentimes, things like carbon dating or depletion of radioactive isotopes of, say, uranium or plutonium or anything like that. It's just another way of measuring the decay rate, really. So an example, we'll make up this new vihelonium. So suppose a certain isotope of vihelonium decays at a rate of 0.1% per year, or 0.001. If we start with 40 kilograms of this stuff, how much are we going to be left with after 38 years? We also want to know what the half-life is. So what we'll do here is just first set up our equation for exponential decay. So y being the amount that we're going to be left with after a certain amount of time. We're starting with 40 kilograms. That's our initial amount. And then we're going to be multiplying that by 1 minus the decay rate, which is 0.1%, or 1/10 of 1%, or 0.001 to the power of x, where x now is the number of years. If we want to rewrite this as just doing this actual calculation of 1 minus 0.001, leaving us 0.999, that's totally fine too. But the whole idea is we want to know how much we got left after 38 years, so that's just going to mean we plug in 38 for x and see what y becomes. Y is equal to 40 times 1 minus 0.001 to the power of 38. And we can do that calculation right here. 40 times 1 minus 0.001 to the power of, oops, I think I accidentally hit negative sign. 40 times 1 minus 0.001 to the power of 38 now. And we're going to have about 38.5 kilograms. After 38 years. So not much has been decayed because, well, our decay rate is so small. It's only 1/10 of 1% per year. Now, as far as half-life goes, well, now we want to know, well, what value of x is going to decrease our initial amount by a factor of 1/2. So we really want to know is, well, what value of x will give us a y of 20? Minus 0.001 to the power of x. And so we want to know what x will give us a y value of 20. So really what we need to do is solve this equation here for x, or undo what's being done to x. Unfortunately, that involves logarithms, which we aren't going to get to until Algebra 2. But what we can do is just look at a table of values that your calculator will, of course, give to you. So if we go back to our y equals, clear that out. We'll put in our exponential decay model here. 40 times 1 minus 0.001 to the power of x. Now if we just look at a table of values here, well, start off with 40, and then we're decreasing down, 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 down. And we could just scroll down, scroll down, scroll down. But this is taking forever, and we don't want to just spend our whole day scrolling. So what we could do if we wanted to is just change up the table set and just start our table at a different value. And we start at, see, table start. Instead of starting at 10, let's go up to 1,000, see what is that. Oh, we went a little bit too far. So after 1,000 years, we're down to a little over 14 kilograms. So let's go back here, maybe try 500, split the difference there. Whoops. 500. Oh, okay, that's not too bad. A little bit, we're still at 25, so we're not there. So it's down here. Let's try maybe 600 or 700. Let's try 700. Why not? Oh, we're really close here. Okay, but we're below 20, so it's got to be up here somewhere. Ah, there we go. So we first get to 20 kilograms somewhere in between year 692 and 693. So the half-life is between 692 and 693 years. Well, what would happen if we started off with a different initial amount? Perhaps that's going to change things. So let's say we started off with, say, just 10 kilograms. So we just change up our model to 10 times 1 minus 0.001 to the power of x. And we'll just look at a table again. And we'll see where we're going to end up with a y value of 5 kilograms. And, oh, hey, wouldn't you know it? Between 692 and 693 years again. So that's the big idea here, is that it doesn't matter what you start with, the half-life is always going to be the same for any given substance. So really, half-life is just another way of expressing the decay rate. It just provides us with a little bit of a different perspective on the situation itself. Now, that's pretty much the basics of exponential decay. So I'm going to leave you with a couple of practice problems right here. So work on those, and we'll go over these next time in class. Enjoy.